Good afternoon, everybody. I want to really thank the organisers for inviting me. The enthusiasm outside the poster session for research and science has been really powerful. I'm really happy to be here and to talk to such enthusiastic people. Thank you very much for the invitation. I want to tell you something about our recent work, advances in I guess I could call it PET MR imaging here. PET MR imaging in humans. So we're really at the man end of your title. 3 Tesla and at 9.4 Tesla. I'm pretty sure I don't need these slides, but I like to use them anyway. There are a few people who don't really appreciate the strengths of the modalities. We use this little fingerprint diagram here. The further out you go from the origin along any particular axis, the better that attribute is fulfilled. So with MRI, we can depict anatomy really beautifully. We're also not bad at showing you function. Temporal resolution, we can produce images in 100 milliseconds if we so choose. Spatial resolution is very good. Despite the fact that it's a very mature modality, the developmental prospects are still great. It's mature at 3 Tesla, widely available, lots of clinical applications, but we're not very good at molecular imaging. Our sensitivities are rather poor. It's the other side of the coin that says we're non-invasive. If you're non-invasive, your interaction between the radio waves and tissue is very small, and we're not that specific. If you look at the same attributes for PET, you'll see PET is very good at function, lousy at showing you anatomy, temporal resolution is poor, but it's the gold standard for molecular imaging, as you know, very, very sensitive, 6 orders of magnitude, probably better than MRI, and very specific depending on the tracer that you might have chosen. Put those together in one machine simultaneously, and you're sort of getting there, but you still don't have the temporal resolution. And one of the things we would like to work on is studying the brain. We need the temporal resolution. Snapshots of the brain is really not going to get you very far. You really need to be able to look at dynamics. If we look at EEG, again, not very good in these areas, but it's got exquisite temporal resolution. And if you can do all of those in one machine, I don't think you really have it. I won't have time to show you any results from EEG, but please take my word for it. We do it routinely at 3 Tesla in the MR PET. And I think I took out the slide. We have started work at 9.4 Tesla as well. So those were my marketing slides, but I think we're all convinced that these hybrid modalities are the way to go. I'd like to begin at 3 Tesla. So this is what our scanner looks like. Some of you might not have seen such images. It's a standard 3 Tesla trio. Inside we have the brain PET, and then inside the brain PET is a transmitter coil, and inside the transmitter is an 8-channel receive coil. So very compact. If you are claustrophobic, you won't like this machine. But when you run it, you can get these sorts of images simultaneously. So you see FDG PET, any sequence of your choice you can run, flare sequence, MP range. UTE is something that you need. I'll come to that a little bit later. So just to give you a little view of the PET insert, this is what it looks like. 32 cassettes screened to prevent MR, the gradients and RF from messing things up too much. And I wanted to just put this slide in, because these really are first FDG images that we acquired. I think it's about 2008 or so. Just to highlight the fact that we have an iterative PET image reconstruction method also. And you can see beautiful resolution here. You can identify even the gyri in the PET image itself. Of course, you acquire the MR, and fusion of the images is then pretty straightforward. When we got the prototype from Siemens, there was a lot of work to do. As you all know, PET is quantitative. Without a transmission source, This machine is not, so we had to do a lot of work to make it quantitative. And this is just a list of the issues that we have to address: randoms correction, scatter correction, attenuation correction of head, normalization, motion is also an issue. And I'll talk a little bit about the MR interferences that you get also. So again, this is the schematic of the detectors unrolled, and you get some map like this, clearly not satisfactory, and we have to do something to correct that. Also, we need to take account of the fact that we've got an RF coil inside the PET detector. There's a CT template of the coil. There it is, somewhat smooth, and a similar template obtained from the standalone HR Plus scanner. Dynamic correction, if you use a global correction, see it's still not performing that well. Just a block-based correction is doing better, and block-based plus pile-up correction, I think now we're pretty happy with these corrections. We did some validation studies in Phantom, so this is again the coil setup, Phantom with some radioactivity in it. And if you look at the decay, see a nice exponential, and if you look at the decay corrected activity over here, and measured activity is the blue line. So that's looking pretty good. So then you think, well, okay, I can now turn on the MR scanner and see what happens. Well, you do that, and you turn on the gradients, and this is what happens to your counts. Different repetition times of the sequence that we were testing out. Actually, not even the sequence, it was just the X gradient, Y gradient, Z gradient. And you see how the count rate drops instantaneously when the gradients are switched on. Not what you want to have. And then we examine that in a bit more detail. So there's the gradient ramping up, steady, and then ramping back down. And this is the PET signal. You can see it's actually at the point of the turnarounds that you're getting the worst effects. And we investigated that in much more detail, looked at the influence of the RF as well. And that's pretty much under control. And we have to come up with ways of correcting for the count rate drop. So here's running an MP rate sequence. You see the count rate drops, remains, and then comes back up. We run the UT sequence, it drops and does other things. And what we found was that this effect was very, very deterministic. We could reproducibly measure it, and so we just took the easy way out. Instead of re-engineering the whole PET scanner, we just programmed a correction factor, and once the count rate is corrected, it looks like that. The issue of quantification is also important, and when we got the prototype scanner, we had to run the machine in the framework of a clinical trial. Patients would come for a PET scan. They would go, first of all, into the HR Plus, the standalone PET scanner, and then they would come into the hybrid scanner, and we needed to show equivalence to convince the authorities that actually this prototype was useful and that we should be able to use it. Once we were out of that, well, we acquired about 100 data sets and convinced the authority that actually the brain PET was better than the HR Plus, so they allowed us to switch it around. And one of the reasons we wanted to switch it around, first of all, was also to look at quantification. And you can see decay. We take the subject out of the hybrid scanner, there's a pause, they go into the HR Plus, the standalone PET scanner, then you can see that the curves match up quite nicely. Allowing you to do quantification of energy consumption then with the brain PET also. And there are some results: quantitative energy consumption of the human brain. This is the MR, glucose consumption, and fused images. So I just want to point out quantitative. So we've overcome the issue of not having a transmission source in the magnet, and we can get quantitative results from PET. And we are now running, so created a complete workflow, FDG, flumaxamil, FET, various other traces, lots of different studies running with these traces in the hybrid scanner. So the corrections that we've looked at the moment, quantitative PET imaging from CATs, parametric images, corrections designed and implemented, for example, for the gradient-induced distortions, an integrated workflow, quantification errors have been determined in phantom studies, and human studies are now being carried out, and we're looking at the long-term stability of the scanner also. So here you can see the bias. This is a slide that's been produced by one of our PET people. He's got wonderful PET images down here, and if you look at the MR, rather inhomogeneous images. They shouldn't be homogeneous. They're pretty homogeneous 3 Tesla. But nevertheless, the hybrid scanner runs in this way. You have the PET scanner running for 50 minutes or so, and during that time, you're at liberty to choose whichever MR technique that it is that you would like to run. We do this routinely now at 3 Tesla, and just to mention, we do this with EEG integrated also. I don't have the results here. Well, I do have the results, but I don't show them to you. It would take too long. So when we got to this stage, we then said to our clinical people, okay, here you go. You can use this scanner in the way that you use the old PET scanner. And this is just an example of the work that we did during the clinical trial. So it's tumor patients. You can see the MR, the 3-dimensional so-called MP-RAGE sequence. And you can see what I mean about specificity. We're not too bad in terms of sensitivity. You can see there's something amiss, but what it is, don't know. Look at the PET data that are acquired simultaneously with FET, and you can see tumor extent really beautifully delineated. While the patient is in the scanner, you ask them to do a so-called finger tapping task and run your favorite fMRI sequence, and you can localize bold activity from the motor cortex. And there's the motor cortex shown here. The fused image is then delivered to the neurosurgeon, who's delighted. He knows now there's the motor cortex, pushed somewhat back by the tumor mass, and the patient can then be operated, and the surgeon has some degree of confidence about where various structures are. We can go one step further. We have DTI, of course, and you can map foot area, hand area. You can show the tumor with FET, and then you can also track the major fiber pathways. There are a lot of clinical studies going on, as I mentioned already. Here's an example of treatment monitoring, the tumor prior to treatment, post-treatment, and various other studies. Given that we've got the hybrid instrument, we can run 2 measurements together, and one of the things, one of my clearly stated goals is I, as an MR researcher, would love to learn from PET and see what I can implement in MRI, what can I steal from PET and do it with MRI. And one of the obvious things is you really want to be looking at arterial spin labeling methods to get cerebral blood flow. We did that. Started the experiment, started the MR measurement, takes about 7 minutes. In the meantime, we do it in about 4 minutes. And then a few minutes into that, you give a bolus of 15 labeled water, get the perfusion map from PET, get the perfusion map from ASL, and you see they're very, very similar. Some local differences, as you can see here and here. We're investigating those local differences because we believe there's quite a bit of science in those local differences. So they look pretty good. We ran the protocol on 10 subjects. These are average results. PET results averaged over the 10 subjects. ASL results averaged over the 10 subjects. And if you look at the quantitative values, pretty good agreement between the 2 methods. So I think this is really nice now. We can stop using O15 labeled water to give us perfusion. As you all know, if you're interested in, for example, receptor density mapping, you really need to know what the blood flow is if you're going to get accurate measures of that. You can now start to use MRI for that blood flow measurement, and you don't have to do it just the once at the start or at the end. You can really do it quite a few times during the course of your PET measurement. So really the idea here is to push PET up into areas where MRI simply can't go, and take over, if you like, the mundane measurements of blood flow with MRI without the radiation dose. I promised you that I'm going to talk about 9.4 Tesla as well. There's a lot of work on the roads to 9.4 Tesla, but also development of methods, my interest, for hybrid MR-PET. These are a couple of methods. Actually, it's quite old now, 2001 that I wrote the first paper on it. We've since resurrected it because we think it's going to be very, very useful at 9.4 Tesla. What is it? It's echoplanar imaging with keyhole. And having said the word keyhole and explained it to you once, I'm not going to use it again because it's fallen into disrepute in the MR world. And actually, I don't use it as a keyhole. I'll explain the differences. So, as you know, our beloved K-space is related by the Fourier transform to real space. Part of it looks like that. If I Fourier transform that, I get my MR image. So that's, what do you call it in the US? MRI Basics 101 or something? Yeah, there you go. And that's done. What happens if I just take the center of K-space, the so-called keyhole? What kind of image am I going to get? Well, actually, it's not a bad image. It's that. Low resolution, but the majority of the contrast, actually all of the contrast, is in that image. You don't have these are the high spatial frequencies, which give you edge information. You don't have that, but you've got the contrast. So the idea behind EPIC, echoplanar imaging with keyhole, was to say, let's acquire this central region, often, but the periphery, if I start in the acquisition, I acquire the solid line, jumping some lines, and then I acquire all the lines in the central region, and then start skipping again. Once I've done that, I store those data, I come back to a second acquisition, acquire the dotted line, jumping 3 in this case, I acquire the whole of the central region and start skipping again, store those data, come back to it another time, and acquire the dashed line, and after 3 shots, I've got the periphery, the edge information acquired once, and I've got 3 times the central region. Now remember, your contrast information lives here. That means I've got 3 independent measures of the contrast, and I can share these lines between those 3 images. So I do a reasonably sophisticated reconstruction. I can reconstruct 3 images where the central region is unique to each one. So if you like, I'm trying to measure the bold response. The bold response is unique to each one, and the edge information is shared. But because I'm acquiring fewer lines in each shot, I get through this quicker, and that brings a lot of advantages. So to get away from this keyhole problem, the old keyhole method acquired a full K-space as a reference K-space, and then acquired only the keyholes in a time series, and they were superimposed. This is just a high-resolution image superimposed with a low resolution. This is not what we do. What we do is in the 4th shot, I've color-coded these white, black, green. The 4th shot, we throw away the first one and reconstruct only images from these 3. And we keep sliding along. So effectively, we have an apparent update rate which is much higher than the real update rate of the high frequencies. So you're going through K-space quicker, which is very advantageous, and you're acquiring more images in the same period of time that you would normally do. Going through K-space brings you this benefit. If this is EPI, you see the susceptibility dropout, signal loss, the frontal, prefrontal regions. And because you're going through quicker in EPIC, much less signal dropout. This is going to be really advantageous when we go to high field, because the problems there are just worse. This is a figure from the original paper. We just put the student who was doing this work, put him in the scanner and flashed some lights at him. Said, okay, we can see visual activation in both. That's good enough. Let's move on. And we did for about 10 years. And then we came back and thought, oh, we really need this technique again. These are now 3 Tesla results acquired actually just a few weeks ago. We really want to push the resolution. 1.25 millimeter EPI, 4 millimeter slice thickness. Only 28 slices are possible in this repetition time. And you see visual activation, but it's not as good as if you do it with EPIC, where you have a higher resolution, 1 by 1, and you can, in that time, acquire 32 slices. And you see the activation is following the gyride to some extent, even at 3 Tesla. And the clear aim is to implement this method in the hybrid scanner and then also modify it further for 9.4. So let's have a look at what we're going to do at 9.4, because it's still a challenge. That method just wouldn't hack it. We need to accelerate. This is your EPI K-space. If you look at the image that results from that, you can see that the temporal lobe's been distorted, because that's what EPI does in those regions of the brain. If you go to EPIC, because you're applying less lines, you should be somewhat more immune from those problems. You can see that there's much less distortion and indeed much less signal dropout. And then you can go and accelerate EPIC even further and get some more advantages out of that. It's this method with a few more modifications that we're going to implement at 9.4 Tesla to make it really quick to get through that K-space. But we had some thoughts about what we want to do with this. Actually, the work is old, but new thoughts about what we want to do with this at 3T. We'd like to measure the arterial input function using dual EPIC, so it's acquiring 2 images in the same acquisition. These are the images, so this would be a T1 weighted image, a T2 star weighted image, and what you can see here, the distortions are back for a number of technical reasons, but the same sorts of distortions in both images, so they can be co-registered because they've been applied in the same sequence. And as you go through, of course, the contrast agent comes in, and we can look at the arterial input function from EPIC. You see a much bigger effect from the first echo, and then the green from the second echo, compared with the red, which is the standard EPI technology. So more information for the same price. But we're still interested in accelerating. Temporal resolution is an issue, and especially at 9.4 Tesla, relaxation times are even shorter, so we need just to get a move on. There are methods called multiplexing now that have been resurrected, and we've implemented those. Also, what is multiplexing? Well, when you acquire a 3D data set with EPI, you acquire 1 slice at a time. That's 100 milliseconds, that's another 100, another 100, and so on. And that's how you go through 4 slices, 4 repetition times. Multiplexing allows you to note the RF pulse now looks different. This is if you like, an RF pulse that is simultaneously going to excite 2 slices. And we apply a second RF pulse, which will also simultaneously excite 2 slices. So you get 4 slices in 1 TI. You've accelerated. The problem is, those 4 slices are all superimposed on top of each other, and we need some sophisticated algorithms to separate them out. But that's in the literature, it's pretty straightforward. So we're going to multiplex EPIC as well. I don't have those results to show you at the moment on our phantoms. We've looked at perfusion maps with EPI, multiplexed EPI, multiplexed EPIC also. So the problem here is we want to measure perfusion, but our slices are relatively thick because of time. If you multiplex, you can improve the resolution also in the Z direction. So here are the results. This is looking at the single band, so effectively the normal method. You can see in the transverse images they look very nice, but they're quite thick slices in the Z direction. But because you can get a factor of 2, 3, whatever it might have been, I don't remember, the resolution in the Z direction also improves in the same acquisition time. And these are very recent results from the fusion thing in the hybrid scan. So that's, I think, pretty much all I want to say to you about the 3T work. So we have the scanner running. It's been running for about 3 years or so. We've done 600-700 subjects, patients in that scanner. And we're now porting that methodology to high field. This is a 9.4 Tesla magnet on its way into the building. Sadly, it's going to have to come out also because it quenched a few months ago. But nevertheless, we managed to do quite a bit of work on it before it quenched. The magnet is a huge beast, weighs 57 tons. It's shielded with 870 tons of iron, floor, ceiling, 4 walls. quite an engineering challenge. The amount of energy stored in the magnet, this is the kinetic energy equivalent of a Boeing 747 traveling at 200 miles an hour. A lot of energy. As you say in German, Steckdose geeignet, you just plug it into the wall, leave it for 2 weeks and it goes to 9.4. It comes complete with hybrid MR PET capability. So the same PET insert, or it can do whole body, but we don't. We're only interested in the neck upwards. So that's showing some results from the 9.4, starting of course with structural imaging. In our institute, traditional brain mapping is a very big area of research. We just want to get the highest possible resolution, regardless of the acquisition time and so on, that we can manage. We started with a post-mortem brain, and it looks like this, 120 micron isotropic. I have to emphasize that for the MR people. This is isotropic voxel size. You can see beautiful grey-white matter contrast. You don't need segmentation algorithms anymore. And if you look at the hippocampus, beautiful layering structure in the hippocampus, and you can even parcellate the hippocampus just based on the layers that you can see. This is a sort of, this was a long acquisition with a very, very bad coil. We think we can do this kind of work in a few hours of acquisition time. The sort of resolution that we'd like to reach in vivo would be something like 200, maybe 250 microns isotropic, and that we estimate from the results we have would be about an hour and a half of acquisition time. So just for traditional brain mapping, what we call, this is what we would be terming as MR histology. We're already approaching that kind of resolution, and we'd like to do in vivo high resolution imaging on that machine as well. So we started. These are 0.5 millimeter isotropic resolution images, short echo time and a somewhat longer echo time. And you can see a number of things pop out, probably not to people at the back, I have to point them out to you. You can see beautiful layering in the cortex without having tried very hard. It's just a standard gradient echo image. You can see the optic radiation, no diffusion weighting, it's just there, you can see it. You can see lots of other structures in these images. Inflow, in the vein there. And of course, we have lots of other results, but I don't want to share. I'd like to get to the MR PET part. The brain insert we got was the same components for the 3 Tesla insert, but delivered as components. We put the whole lot together. One of the first things I wanted to do, being an MR physicist, positron, charged particle, you should get an improved resolution in the PET. I talked to my PET colleague and said, no, if you're just a physicist, it won't improve. And we had this debate for a while. And it turned out that both of us were right. For fluorine, the improvement is really minimal. You get a small improvement up to about 3 Tesla, and there's nothing more. But for the high energetic emitters, you can see the difference between 0 and 9.4 Tesla. You get an improved resolution as well as somewhat improved contrast, just to blow those up for you. All the details are in this paper over here. And now you can see the 0 Tesla emitter, the PET insert outside the magnet compared to being at the isocenter of the magnet. It's just a thing while we were waiting for regulatory approval we wanted to do. While we were waiting for regulatory approval, we also wanted to test the hybrid capability of the scanner. And this is a F18 fluoride scan of a rat, acquired in the 3T brain PET, acquired in the dedicated animal PET, the Invion, and these two required simultaneously. And you can see that there are no visible artifacts in the MRI, and the PET is very comparable to the other instruments. So we're pretty much ready to do hybrid imaging. If we could get our 9.4 Tesla field back. What are the opportunities in this 9.4 Tesla hybrid scanner? Well, I think I've demonstrated, I hope, that the high spatial resolution is very useful for structural imaging. Bold, the blood oxygen level dependent mechanism, scales with the field squared, so we should really be able to win handsomely, and we think we should be able to achieve sort of columnar resolution fMRI. Image quality, the contrast is simply richer, and I'd like to talk to you a little bit about these areas in a moment. PET, well, there are a whole host of things that PET can benefit from simply because MRI is there, providing things like motion correction, navigator echoes, attenuation correction, partial volume correction, a whole host of other things. But when you put the two together, this is where I would like to go. Metabolic imaging, you have PET as the gold standard for metabolic imaging. For example, the most simple thing you can think of, FDG. And we can get a handle of these nuclei, oxygen, phosphorus, sodium, and all of the standard MR sequences as well. If we could do that, for example, with the blood volume measurements, blood flow measurements, accurate receptor density mapping really becomes possible. And here's the challenge for us as a community, I think. You can't simply take a functional paradigm, the so-called block paradigm, where you tell people to tap their fingers, rest, tap their fingers, rest, and so on. You can't simply take that into a hybrid scanner and run a PET scan at the same time and think you're going to do anything useful. We really need to start putting our thinking caps on, thinking about novel paradigms for brain function that you can use in the hybrid scanner. And it may well be initially that we explore different aspects of a problem with the two modalities. Metabolic imaging, I mentioned that we're talking about this triple modality with EEG. We really want to get a handle on, for example, delta band activities, which correlates very strongly with metabolic activity in the brain, so that we can actually integrate all of that also. Why sodium? Well, sodium-potassium pump, I think everybody knows disturbances of the pump often lead to cell death. And we're very interested in looking at intra versus extracellular sodium without injecting the toxic contrast agents, but doing it with triple quantum filtering. We've done that. We have a sequence which allows you to acquire the total sodium concentration and the intracellular all in one sequence without having extended the measurement time. I won't talk about that today, it's in the literature. Phosphorus, energy metabolism of the cell. It's one of the few ways that you can get an in vivo pH non-invasively. So my mantra is really in vivo, non-invasive throughout the presentation. Oxygen, I think I'll say much more about that. And glucose, the energy substrate of the brain. We heard Sarah's talk this morning. I don't have C13 capabilities, so it's not on this list. I'd love to have it on the list. Show you some sodium results. Just a proton image just to orient you at the anatomy, acquired at 4 Tesla some time ago. And if you look at a 4 Tesla sodium image, not great. There's not very much sodium compared to the proton. It's not compared to water, it's not very much. But it's a high resolution image, 2 millimeters isotropic, acquired only in 15 minutes acquisition time. We took the same sequence, implemented it at 9.4 Tesla, and this is what you get at 9.4 Tesla. And this is now, I think you'll agree, a significant improvement. We programmed and examined a number of different techniques for measuring sodium, settled on this one here, twisted projection imaging, and we ran that 2 millimeter isotropic again in 7 minutes acquisition time, and these are the sorts of images that you can get of sodium. So it's the sodium distribution, nothing to do with water anymore, it's the distribution of the sodium ion. Oxygen, we've started work. The one big problem with these so-called X nuclei, anything other than a proton with MRI, is you're really making life even more difficult for yourself. The signal-to-noise ratios are really lousy, and oxygen has a natural abundance of 0.037%. Really not much of it around. But if you think about metabolism, water is the end product of metabolism. It would be really nice if we could just look at normal water and look at fluxes and get a handle on metabolism. Unfortunately, we've got this 80-odd% background signal, and we're just not going to be able to pick up the small changes in normal water. If you can label well, if you label water with O17 injected, you have another perfusion tracer, if you like, but that's not what we want to do. What we'd like to do is to get the subject to breathe in oxygen 17. Now, oxygen 17, when it's a gas, its relaxation times are very, very short. We don't see it. Unlike O15. When O17 is attached to hemoglobin, the relaxation times are also very, very short. We don't see it either. It's only when O17 goes through the metabolic cycle and ends up in water, H217O, then we detect it. So we can really get a handle on CMR2, for example, by using O17 as a tracer. So I think I will just carry on some of the things that I'm not going to show. So what we're going to do, that's there, thank you. So these are natural abundance, very low SNR, and when we allow somebody to breathe O17, then of course the amount of water labeled with O17 is going to increase, and those are the changes that we want to be able to pick up. So why all this blather about different nuclei? Well, here's the sodium-potassium pump. This is what phosphorus allows you to detect, ATPase, oxidative phosphorylation and so on. As I mentioned, we don't have C13, but O17, you can get a good handle on this one. So for looking at CMR02, we'd like to have a method that's accurate, reproducible, suitable for patients, non-invasive or minimally invasive. Method should really have potential for widespread use. There are too many 9.4 Teslas. I'll deal with that. And you shouldn't require an on-site cyclotron. And that's why O15, although we have an on-site cyclotron, we think that O17 might be the way to go. So there's the 9.4 Tesla scanner with the oxygen coil, sequences programmed, the breathing apparatus programmed, the so-called flex twisted projection imaging acquisition, all programmed. And we really need to address that issue of quantification again. If you're going to, try to be quantitative, you really need to know correct for tissue mass, and you can do that from the water maps. I'm not going to show you the water maps, but we can acquire quantitative water maps to accuracy of percent in reasonably short acquisition times, and then we can correct for tissue mass. And knowing the water concentration is also actually quite important for proton spectroscopy, which I'll deal with. We've been developing a lot of sequences, or reprogramming actually is more accurate. Sequences in the literature at 9.40. So we want to try to detect glutamate, glutamine, GABA. We're running a couple of studies actually at 3 Tesla, looking in hybrid mode. I'll show you this example also, and want to do some work at 9.4. 2-hydroxyglutarate in tumours. We want to be able to detect that with normal proton spectroscopy. So this is the hybrid scanner again, PET, MRI. And you can see the spectroscopic measurement, you can see the peak from 2HG very, very clearly. 2HG is normally only present in vanishingly small amounts, except when you have these mutations, published in the paper in Nature by Choi et al. And we can show that it's detectable in, even at 3 Tesla very, very easily. You can go further and sort of classify the tumor. And with the FET scan there also, see the delineation of the tumor. And then if you look at how well the 2HG peak corresponds with that, it's a great match with that. All at 3 Tesla is ready to go at 9.40. This is actually the only spectrum that we acquired before the magnet said goodbye. Proton spectroscopy at 9.4 Tesla, you've got about 15 metabolites here you can reliably get compared to about 5 or 6 at 3 Tesla. 3 Tesla results for proton, for phosphorus spectroscopy, excuse me. You can get pH from the separation between these two lines, gamma ATP, alpha ATP, beta ATP. in spectrum. And what we'd like to do, what MRI allows you to do, is to try to get some of these rate constants by selectively saturating a peak and then allowing it to recover again, and doing some fitting to get the rate constants that are shown here. This is work that's all prepared and ready to go at 9.4 Tesla with the quantum sequences programmed. So for aerobic respiration glycolysis, you have a handle on glucose, a handle on ATP, oxidative phosphorylation, you have a handle on ATP, and so on. And these are the sorts of things that we'd like to get out of spectroscopy. I want to conclude by thanking all of the whole institute. Actually, it's a joint activity between the different groups here in the institute. And I'd also like to thank you for your attention, and just point out that we're a government research centre. We welcome visiting scholars, scientists, postdocs, graduate students. Thank you very much.
So I think we have time for a few questions if you have any.
I'm curious about the reason for having in the keyhole for having the full sampling of the reading code in a certain direction.
In the keyhole, having
The full range of the reading code direction.
because you want to have in the read direction.
Yes.
Now that doesn't cost us very much time, but there are methods. There are methods that also shorten that. In the read direction, we're reading each line 750 microseconds or so, maybe a millisecond if we're really pushed for this enough. So your artifacts don't have that much time to develop in that direction. In the other direction, when you're reading 64 of them, you're reading for 64 milliseconds, and then you get the problems here.
How much does a 9.4 Tesla scanner cost?
This is a prototype scanner with the PET and hybrid as well. It was 20 million euros. 30 million dollars.
Did you have any input in the design of it, or was it mostly the company?
Mostly the company. So the scanner is, if you like, three major component blocks. There's the magnet and gradient coil. Nobody in their right minds will try to do anything there. It's just too expensive and takes too much time. Then there's what we call the console, the gradient drivers, etc., etc. And there, the companies have spent a lot of time optimizing those. Couldn't really mess around there either. And then there's the other block, which is RF coils and the pulse sequences. We've done that part. And then, of course, the integration of the PET insert into the environment. I think I didn't mention it on my previous slide. Siemens and BMDF. That's the Industrial Science Education. They funded the scanner job. Sorry.
So, if I may ask, did that 20 million euros include installation, or is that just for the?
That's just the scanner.
How much was the installation?
Actually, in comparison to these numbers, the installation wasn't very much. We built quite a large building. That was 5 million euros, including the iron, the Faraday shield, everything. So it wasn't too bad. I can't see because of the spotlight.
So I'll just
There's a
speak.
question.
You said the integration of the PET insert. Was there any significant difference or a major change necessary to actually make it work in the 9.4 versus the 3 Tesla system?
No major change. We had discussions about this prior to receiving the components from Siemens about what kind of thickness of copper should be used to shield the cassettes. And my view was either frequency, the thinner the skin depth, just give me the 3 Tesla one stop is fine, at 9.4. And indeed, that turned out to be the case. We spent probably the best part of 2 months or so doing that, and the biggest problem was actually an earthing problem. So we had these ground loops, and we just had to find them and sort them out. But basically, there weren't any major issues.
Okay, well, thank you so
Thank you.
much.